Hello, legends. This is Mr. Maze coming to you through the virtual space. And today, wonderful as it is, we are looking at the Unit 8 Pro Tips. And as you know, Unit 8, this is the big one. This is the big fish. And we're going to take it and we're going to pluck from it all the meaning and inference knowledge that we need. And I'm going to try and just go through this list of different things I'd like you to spend some extra effort and time on. I'll give you a hint or two, but of course, for the most part, it's stuff that you just need to procedurally work on, just like the speech I gave you in class, and like everything we've been pushing all year. This is a practice in how to think and how to go about refining thought. So know the different methodologies as well as you can. My tips are as follows. Number one, read closely. This is an obvious one. And it may feel like a give, right? It's like, oh, that's not even a real tip, but no, truthfully, there will be questions here where knots are important, where understanding if we're looking for the null or the alternate, or understanding, maybe where the sign is that we need to set when setting our alternate hypothesis can be important. And understanding all of these little intricacies is what's going to allow you to ensure you're getting the right answer. So just like with Unit 7, when hypothesis test stuff and significance test stuff, for the most part, led to you having to read very closely to set up your nulls and alts correctly, and also to be sure that you're looking for the right things. This will come into play again here. Okay, number two. And you know this. I'm going to call this Know Your Methods. And per that, know your calculator, right? Know the functions. The main functions you're going to be using on this test are as follows, and this will not surprise you, right? Oh, and actually, this is not its own thing. This should be under calculator. The most common ones that you're going to be doing are 2samp. Ooh, not Z. What am I doing? 2samp. Ooh, T int for confidence intervals for means. 2samp T test for significance tests for 2 means. You will likely see a paired t-test. So remember to know that a paired t-test is always dependent, and I'll go on in more detail on that in a moment, but that it runs like a 1samp t-test. So keep that in mind. And this is all to say, you may have to do a 1samp t-test or a 1samp t-interval. You may also have to do a 1prop z-test or a 1prop z-interval. And that goes into our other functions, right? 2prop z-test for significance tests for 2 proportions. 2 sample proportions, I should say. And 2prop z-int if we're doing 2 sample proportional difference for an interval. So know those functions and know how to function with them effectively. And then, of course, as a part of your calculator experience, you'll want to know how to mess with data. So know how to go, to stats, data, plug in L1 and L2, and then take that data, and refine it into going into stats, and always, always, always when it's data, running one of the t-related tests, right? Either a t-test or a t-int if we're looking for an interval. Because you're not going to do L1 and L2 when you're doing proportions, because proportions, you just find the proportion, the p-hat, and you roll accordingly. Okay, legends. All of that should make good sense. And know those, as I always say, inside out and backwards. Know all their intricacies. Okay, a little more detail as to what's to come. Part 3. Remember that, two-sided, and this is going to sound very obvious, but bear with me here. Remember that two-sided is greater or less than, remember that two-sided is different and one-sided is greater or less than. So remember that if I'm doing a hypothesis test, a significance test, remember that if you see, is the thing significantly different, that does not equal, and that is inherently a two-sided test. And then remember, on the other hand, right, that if it says greater than or less than, that's going to lead to, again, greater than or less than, which is a one-sided test. And remember that the p-value for a two-sided test is equal to 2 times the p-value for a one-sided test, as long as it's from the same sample data. And that should make logical sense, right? So if we imagine a graph of the data and we are looking at a sampling distribution based off of that data, and we run a two-sided test looking for both extremes, that's just equal to 2 times one of those sides, which would be 2 times the one-sided version of that test. And that may indeed come into play in some of your questions. Part 4. I want to talk a little bit about paired t-tests. I want to make sure this is clear. Paired t-tests must be dependent. Now, the ways those dependencies show up are various, but be aware that they're always dependent. And when I say they're always dependent, I mean like things like before and after come up a lot. So the same person or set of people, and we look at their results on something before and then their results on something after a particular treatment. It could be like twins. It could be spouses, right? I'm taking, partners. Those are all situations where we have inherent dependency, right? If I picked one spouse, I had to pick the other spouse in the other group. They are dependent one on the other in the way that I very much made the pairing. So think matched there. They're matched pairs. And that's the key here. It's not just that they have to have the same number of values in each group, which they do. It's that I have to see a dependency there. And the big ones you're going to see, again, are before and after. Spouses are a big one. Twins. I'm trying to think of anything else. We did one that was litter mates. That's also true. But make sure, and this is how I think about it, there's like a clear connection between a singular value in one group and a singular value in the other, right? And that's going to be matched pairs. If, on the other hand, we're thinking, well, what's the difference between that and two-sample t-tests? You can get pretty close to that, but in two-sample t-tests, it's always independent. So it's always like randomly selecting, right? There's no randomness when you're picking twins. I mean, you might randomly pick a particular set of twins, but there's no randomness. Once you've picked one twin, you have to pick the other twin, right? Or once you pick one person, you have to pick their spouse if you're doing a spouses matched pair. Versus with sample t-test, you could do random pairs of people, but it would be random, right? And that randomness is what makes it a two-sample t-test choice. And remember, two-sample t-tests can have the same number of values in one sample as the other sample. That's totally fine. The key here is just that they are independent. Okay, so we have that sort of idea. I hope that has stuck with you. That's very important. And again, random samples are okay. And random pairs would also be considered a two-sample t-test. Beautiful. We're doing a great job. We're making great time. Number 5. And this is going to sound obvious, understand p-values. And when I say understand p-values, obviously I mean be able to interpret them, know that definition, the one that starts with assuming, and then I need you to give me the null is true. I need you to give me context. Don't forget to give me context. That's going to be its own note in a moment to just make sure to give context always, always, always. The odds or the probability of my sample statistic or more extreme are, and then you'll give the p-value. But you should give the actual p-value. Don't just write are my p-value. Okay, so know that about p-values. The other thing is know that if you're running through a variety of different metrics, p-values will be always in reference to how they respond to the null, right? So we're always interested in, with a p-value, if the p-value is less than the alpha or if it's greater than the alpha. And something you should know is that if the p-value is greater than the alpha in a two-sample test, right? Remember that the null hypothesis, if it's greater, right, then we fail to reject the null. Now that part seems obvious, but let me make sure I go into enough detail with you here. We fail to reject the null if the p-value is greater than the alpha. We know this. And we know that the null in a two-sample test is almost always going to be, actually let me do it to the side. Ooh. We know that the null in a two-sample test is almost always going to be, and in fact in this class always will be, let's do means for example, that one mean is equal to the other mean. Also known as, I should say, one mean minus the other mean equals 0. So if we fail to reject that, we should expect 0 in our interval in this particular case. We should also expect, so let me put a couple of thoughts into your heads. We should also expect about, and this goes for if we're talking about a confidence interval here, right? And this is for a p-value where it's like does not equal, right? And if we notice that the p-value for does not equal, and I'm specifically, actually, I shouldn't write that there. I guess I'm saying when I say we're talking about a confidence interval, note that that means this would be in reference to a p-value that is a does not equal. So 2 times a one-sided p-value, right? So if I gave you a one-sided p-value, I was like, oh, the p-value is 0.04, right, for a one-sided p-value. And then suddenly the question started talking about a confidence interval, or what you would expect in the confidence interval. Know that you should multiply that 0.04 by 2, for example, because then it would make it into a two-sided. This goes back to the previous idea. This would make it into a two-sided test, and the p-value would be in reference to a two-sided calculation. Okay, that was just a side note, but it's going to be important, and you'll see those ideas, those very exact ideas, show up on your exam. So good to keep that in mind. So, but in reference to a confidence interval of does not equal, you should view, if the 0 is in your interval, about an even amount of positive and negative intervals, right? So if you were to take a bunch of these intervals and 0 is almost always in them, you would expect about an even amount of positive and negative intervals. And what that means essentially is that 0 is in there, which means 0 is likely. So you would expect your intervals to dip into the negative and dip into the positive pretty equivalent times throughout all of the possible samples you might get. And that should make sense, or at least all of the samples that actually capture the interval. So if it's a 95% interval, we would expect about 95% of those intervals to dip into the positives and the negatives an even amount of time across those two metrics. Now, some other things that we should keep in mind here. If we're looking at different intervals, sorry, I'm like looking at my wonderful notes for you all. If we're looking at various intervals, I want you to be able to run your tests quickly and adeptly. This is going to sound very obvious, but be quick and efficient. Quick and efficient. Magnificently important, right? Because you're going to have these calculators and you're going to have to run all of these calculations that I've stated and referenced up here. So be able to run through them effectively and don't have to stop, right? Know exactly what you're doing and why you're doing it. And that saves you a lot of headache and a lot of time, which is good because you're going to be going and picking apart multiple choice questions alongside FRQ questions. And I want you to know your stuff wonderfully and solidly, right? Okay, so we'll keep that in mind. The other thing I want you to know alongside that is that, and we'll call this part 7, is that if we are doing a two-tailed significance test, that is the equivalent, and I brought this up a moment ago, of a confidence interval at the same level. But what we need to note is, for example, if the confidence interval is 95%, then it's equivalent to a two-tailed significance test, at an alpha of 5%. Okay? So confidence level, right, is equal to 1 minus whatever the alpha is if it's a two-tailed test for significance. Okay? So just be aware of that. There will be questions where that interpretation is important because they'll be pairing them up and saying like, oh, which of these would you find to be the same? Or which of these is true if this thing about a confidence interval is true? You'll have to know how to translate that into a two-tailed significance test and vice versa. There might be something where it's like, oh, this proved true in a two-tailed significance test to an alpha of 0.02. What does this mean? And you'll have to go looking for the things that prove true to 98% significance, for example. So hopefully that sits with you well. And the sense is being made. And I said this earlier, but remember you multiply the p-value for a one-tailed test times 2 to get the p-value you would get for the same sample for a two-tailed test instead. Whew. All right, we've gotten through a lot. There is yet more to go through, but take a moment, breathe, make sure this is all wonderfully clear for you, and we will move ever forward, okay? Okay, so things I want to go over moving forward. We're going to do number 8. Needed to take my breather to check through all of the things I want to touch base with you on. One last thing on number 7 before I switch on to number 8. I wanted to set up number 8 so I don't leave it behind. But one last thing on number 7 that I want you to be aware of. You should be ready for the phrasing of if we're talking about a particular confidence interval or we're talking about a two-tailed significance test or whatever it is, we would expect 95% of the time, right? If we're talking about a 95% confidence interval or a two-tailed significance test with an alpha of 5%, we would expect 95% of the time to capture the truth, whatever that truth is, be it a mean or a proportion, and the other 5% of the time to fail to. So keep that in mind. Those are two different ways, and I should say capture true. Those are two different ways that that same idea can be talked about. And I'm telling you this because when you get to my test, I don't want tiny multiple choice questions where they phrase things differently and they're like, which of these is accurate? I don't want them to throw you for a loop, right? So be aware that effectively what we're saying in like a 95% confidence interval, for example, is that if we did our intervals 95% of the time, we would expect to capture the true proportion of blah, 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 or the true mean, blah, blah, blah. And 5% of those intervals we'd expect to completely fail to do that, right? Similarly, if we did a two-tailed significance test, right, at an alpha of 5%, right, and we, excuse me, pardon me, I had pizza tonight, so the burps are ever present. But all of that said, and I hope you're having a pizza night yourself, mind you, because that's the perfect way to study for Unit 8. But with this two-tailed significance test, if we have an alpha of 5%, we would expect 95% of confidence intervals to the 95% level. We'd expect 95% of possible intervals to capture the truth, right? And if our p-value were greater than the alpha, right? So if our p-value was like 0.08 or something, or 0.1, if it were greater than this alpha of 5%, we would expect 95% of possible intervals to include the value 0. Okay, that's a lot of talking, but all of that should have parsed through to something sensible and meaningful to you. And if it doesn't, definitely go through the previous video notes and then re-listen to what I just said to you. And you'll know that you are in the right place for this tip number 7 when you listen through it again and go, Mr. Mays, that makes perfect sense. I totally get what you're saying. The second part of that, of course, is that you would expect in 5% of those intervals about to fail to capture 0 if it proved, again, that your p-value were greater in the two-tailed significance test than your alpha of 5%. And then we were, again, looking at the corollary of a 95% confidence interval. So number 7 is really about thoroughly understanding the relationship between confidence intervals and two-tailed significance tests, and that will be important on your test. Okay. Tip number 8 is as wonderful as you might imagine. It is literally what you're looking for when you're looking to get past tip number 7, which requires a lot of critical thought. Know how to set up. The null and the alternate hypotheses. Just know how to set them up. It's super simple, right? You had to do it a bunch on your Unit 7 test. Be able to do it now. for this Unit 8 test, specifically for two samples, but just in general, know how to set up your null and your alt. Remember that the null is always an equal equation. It's never anything other than an equals equation, right? Parameter 1 equals parameter 2. That can be mean 1 equals mean 2. That can be P1 equals P2 if we're doing proportions. But no matter how you set it up, it's always going to be that. And then the alt will be greater than, less than, or not equal to, being if it's, one-tailed or two-tailed. Okay. So now we will go on to tip number 9. And what is number 9? Just remember in a confidence interval, right? If you have 0 in a confidence interval, for two samples, right? Just be aware that means no difference. No significant difference. And I hope you're noticing, legends. There's a lot of repetition in what I'm talking about, and I seem to continuously be returning to this idea of interpreting confidence intervals with 0 in them and seeing how that relates to two-tailed significance tests and all of this and how it plays around with our conception, right, of how we use these different tests to understand difference and what is different and what is not different. Be sure to give context and be able to say no convincing evidence for the alternate. You need to give that along with the context for it. All right. We move on now to step 10. Oh my goodness me. Remember the equation formats. For both one sample and two sample confidence intervals. Oh goodness, my F's are hideous. Intervals. What am I saying when I say that? What I mean is remember the setup of the equation for how you solve for a one sample and a two sample confidence interval, right? Know that format and know what values go where. Okay, it's super important to know that structure. Remember that with confidence intervals, you're always working with p-hats or with x-bars, unlike with hypothesis tests where you have like a null proportion, or obviously with two samples, a pooled proportion. But know that as well, mind you, that will be important. Know when you're using that one pooled proportion, right, for a two-sample hypothesis test for proportion specifically, and know with everything else you'll just use the individual proportions, or with the means you'll just use the x-bars provided. But know the equation formats for one sample and two sample confidence intervals, right? So the one sample one, just as a reminder, and I'll do it for means, is x-bar plus or minus your critical value, which will likely be t, right, if we only have the standard deviation for one particular sample, times standard deviation of the sample over the square root of n, for example, would be one of those. Or for one sample, this is all for one sample, p hat plus or minus the z critical value times the square root of p hat times 1 minus p hat over n. Right? So just remember those formats, and then remember the same ones for two sample confidence intervals. The equations will be posted on the review or the equation sheet, but they're posted in that weird way where I have them like written out like sample statistic minus yada yada. So be able to read those effectively and understand those values. And be able to do the same for your two sample confidence interval equations. You should go through those yourself. I'll leave you to go digging for those again because I hate writing those out. It takes so much time. Okay. Ever forward we romp. Remember how to find your z and t critical values. I know it's been a minute, but I'll just throw it in there. Go back into your stuff. Remember how to find your z and t critical values. It's super important. Remember that for both of them, it's going to be inv norm for the z one, and it's going to be inv t for the t one. And just remember how those are calculated. Try it out for yourself with various confidence levels, right? So remember for Z, if you have, and I'll just like briefly go through this, but for Z or for T, if we were doing 95% confidence Remember that for both z and for t, the area that you would be putting in would be the halfway point between that and 100%. So halfway between 95 and 100 would be 0.975, and that's what you'd put in. And then for t, you would do degrees of freedom. And then for z, right, you would do mean and standard deviation. So just be aware of those values and aware of the fact that this is how you would go backwards and determinately find what the z-score would look like or what the t-critical value would look like. Now remember, for the z-critical value, you'll put a mean in of 0 and a standard deviation of 1. Because what you're effectively asking is, what would be the z-critical value on a distribution where the mean is 0 and the standard deviation is 1 at 90.975, right? And then for t, of course, we've just put in the sample size minus 1. But remember how to do all that. Don't get lost. Okay, tip 12. Remember this. This is going to sound so obvious, but actually you should feel relieved because we've gone through some of the more complicated stuff already. Be aware and remember that you need two entire samples for a two-sample test, right? You need two entire samples for a two-sample test. Even for a two-sample confidence interval, you need two entire samples. So, for example, if I surveyed 300 people and I found that 15 of them love beef jerky and the other, 285 do not love beef jerky, which is horrific because you should love beef jerky, I should say. But if I found that, these are not two different samples. This is one sample, right? They're all from the same single sample. I'm just using the two sides of the coin. That's not a two-sample test. Two samples are for two samples. You can't take a one sample and force it to be a two sample. I just want to be clear about that because there's definitely a trick with that in the test. And also AP always tries to slide one past the proverbial goalie, and you're too smart for that. I won't let that happen to you. Just want to remind you of these things. Okay, where are we at? 11, 12. Wow, we are zooming, legends. We are zooming. Okay, so we are rocking and rolling ever forward here. We should also remember binomial notation. This is a really good pull here. Okay, legends. This is a secret for you because you were wise enough to watch my pro tips video, even though it's very long. I'm sure it is. I'm certain right now it's going to be a long one. Remember binomial notation. So this is a shout out for my people, okay? Remember binomial notation where it's total number of trials done over successes, where we go odds of success, so number of successes, whatever that fraction will be, because that will be a fraction, to the power of the number of times we see those successes, right? Times odds of failure to the number of times you see those failures, which is n minus x, right? So just to be clear about that binomial notation stuff, and you'll have previous notes on this way back when from probability in like unit 3, but we're bringing her back strong. There's definitely going to be a cool bonus question in here about binomial notation. Just remember you'll have, for example, if I say I roll a dice, 50 times. If I roll a dice 50 times, and it's like, what are the odds that I roll whatever? Let's say it's a regular six-sided die, and I roll it 50 times. And I say, what are the odds that I get 10 times I get the value 6, right? So I've rolled n equals 50 times. I get the value 6, but I get the value 6 10 times, so x will equal 10. So that means if I'm doing my format, I'll do 50 over 10, right? 10 will also be the power, right? Because that's how many times I'm expecting my value. 6 is one particular value out of a potential. I just said it's a six-sided die. So there's a 1 in 6 chance of getting a 6 when you roll a six-sided die. So that would be 1/6 to the power of 10. This other value I know is going to be to the power of 40, right? Because we're doing this 50 total times. So these two numbers you should remember should add up to that value n, right? And this value here will often be the same as this value. Sometimes it's the other value that they set it up, but the one for the odds of success will match up with your success rate. And then, of course, the odds of getting anything but a 6, which is your failure rate, would be 5 out of 6. Okay, that should make good sense. Just wanted to drop in on that idea briefly so that you're ready for a special question on that potentially. All right. I already said this, but to be very clear, one last time, in a confidence interval, if, for example, 95% of intervals contain the value, that means 5% of intervals do not. I'll spend no more time on that. I'm getting a bit repetitious, but again, I really want to hammer home the ideas that we are rolling with. And remember always that with a confidence interval, it's always the true parameter. We're looking for the parameter, the true mean, the true standard deviation. Never the sample. Read carefully to make sure you are not talking about the sample. We are uninterested heroes in the sample. Okay, we use the sample to create our interval. Ooh, this is so cool. Guys, the countdown is real. 10%. Can we make it? Don't be stressed. We're going to get there, okay? All right. Central limit theorem. I really want to go over this really quickly. The central limit theorem, and the key here is sample data, normal, or population data, normal. If any one of these proves true, then for means, you're approximately normal in your sampling distribution. And you can do all the things that you want to do. If any one of these, if this is right, or this is right, or this is right, you're good to go. So if sample data, and this, I will definitely do something like this. I may do something where the central limit theorem passes, but the sample data is skewed. And you should know, it doesn't matter because the central limit theorem passed. Or maybe I'll show you the population data and the central limit theorem passes. And you'll go, oh wait, the central limit theorem passes. It doesn't matter that the population data is crap, okay? And just like we did a lot this unit, where like sometimes we would look at the central limit theorem and the central limit theorem failed, but then the sample data fixed it or the population data fixed it. Just make sure you're clear that any one of those being the case means you're good to go and you're approximately normal. And if any of the other ones are not, it doesn't matter because that one was the case. We're on 8% legends. Let's make it happen. Tip 16. We're really rolling for these ones, right? Okay, what am I trying to say here? Yep, know all your calculator functions. You know this, right? For your 2 sample confidence intervals, this is obvious. For 2 sample confidence intervals, you're either dealing with proportions or you're dealing with true means. And the same thing is true with 2 sample tests. You're either dealing with proportions or you're dealing with means. Just know all your calculator functions and don't mix them up. Don't do a proportions check for a mean or a means check for proportion. Know how to check for normalcy in means, like we just said for number 15, and then how to check for it in proportions. N times times 1 minus p. And for proportion tests, know that it's the pooled proportion. Don't forget to do the pooled proportion for a 2 sample hypothesis test for proportions, okay? You should know, number 17, the meaning. When someone says, what is the meaning of 95% confident? When you see that, know that they're asking for you to define confidence level. So that's the time when you're going to do, if we did many, many samples, all of the same size, and we made 95% confidence intervals for each of those samples, we would expect about 95% of those intervals to contain the true whatever. Okay, that should make sense. You know that. Always give context when you are doing that. So I didn't give context because I had no problem to deal with, but always give context when you are doing interpretations of confidence level. We're doing it, legends. We're nearly there. 18. All right. You will likely need to take raw data. I'm going to do this to you. That is dependent. Put it into L1. So first you'll have to do subtracting the data. Data from one sample from the other. And you'll know it's dependent. It will say in some way in the question, it'll be clear to you that these are dependent samples. And you will have to go through and subtract each data point from the other. There won't be many of them. It'll be like 10 data points. But you will have to do those subtractions. Oh, we're doing it 5%, Legends, we can do this. You'll have to do those subtractions and then input them in as L1 and then do a one sample. Right? T-test or confidence interval. Right? So one sample, I should say T-int. Okay? Be prepared to do that. Okay? It's not hard, but you will have to do a paired t-test where you are given raw data, and you know that the data is dependent one on the other, so you have to do the subtractions and then input it as L1 and then run all the stats on it. 19, no CSOCs, right? Know how to compare medians from two visualizations. And you should know what I mean by that, right? Look at two visualizations of particular graphs and be able to compare their medians and their shapes and things like that. We went over this. And 20, be able to explain. This is super important to me. What standard error is. So the standard deviation of a sampling distribution. Be able to explain what that is, right? And what sample variability is. Sampling variability. So this idea that every time you take a sample of something, you're going to get a slightly different value, even though you're like jumping around the true proportion or the true mean, you're going to have variability. And that's why we have sampling distributions, so that we can get an idea of what's variable in a sensible way and what's variable in a not sensible way. Be able to explain that to someone and use that to tell them why you can't just use one sample. So if like your buddy's like, I did a sample. One mean was higher on average than the other. I did the subtraction and one value was higher. I did the mean difference on that one sample. I'm good to go. And you're like, no, you have to do a confidence interval and then you have to do a hypothesis test if you really want to check it, specifically the hypothesis test. And he'll be like, why? I did the single sample and I subtracted. And you'll have to say, well, there's variability when you do a sample. So your sample might have varied in a way that's totally sensible, that sits within our standard error of what a sample's variability might be. So that's why we can't just take one sample. We have to do a hypothesis test. And 21, our final tip, we'll end on an odd number here. Be able to use a visual sampling distribution like we did on the last test on Unit 7, the second to last question. Use a visual sampling distribution to estimate a p-value, right? That sort of thing where you were looking at the graph and you were like, the p-value is probably around blah, right? And then obviously use that to either reject or fail. To reject the null. Legends. Never accept the null. Never accept the null. Okay, heroes. I know that was a bit scattered. However, what I will tell you is I'm hoping that these pro tips are becoming more and more like a sort of Alice in Wonderland winding road where if you do your work and you study all of the concepts along and along, coming to these video notes feels like you are walking a wondrous pathway that guides you secretly through the things you'll need to be strong on to do brilliantly on this test. Read closely, know all your methods, understand significance tests, p-values, paired t-tests versus two-sample t-tests, understand how to look at a p-value and compare it to an alpha, know the relationship between two-tailed and one-tailed tests and their p-values, know the relationship between confidence intervals and two-tailed significance tests, right? Know what you're comparing and why you're comparing it, all the way down through all of these things, even a binomial notation problem you will note, right? Know your different theories and your backgrounds, know CSOCs and how to compare distributions, and then how to use a visual sampling distribution to estimate a p-value, right? And be able to explain standard error and sampling variability as to why you can't just use a single set of samples, find their difference, and go, see, there's proven difference. Ta-da. You are heroes and legends. Thank you for going on that mission and that journey with me. We've meandered through brilliance together. I'm so proud to be your teacher, and I'm so thankful for you. Study so hard. Study harder than you ever have. And practice once again learning how to think about what the truth is and how we tackle it every day. Thank you for being my student. This is Mr. Mays, wishing you the best on Unit 8, knowing you will do brilliantly, and signing